people who come in, if anyone comes in late or if you haven't had a chance to hand in your homework, you could do that at the end of the lecture. But don't come up now. Let's just get started here. So I was thinking maybe we ought to stop talking about one-dimensional systems and move into the next part of the course, which will be two-dimensional systems. And so this will occupy us for quite a while. And let's begin with the simplest kind of two-dimensional systems, because as you probably realize, there's all kinds of two-dimensional surfaces we could be talking about. The plane is the most obvious one, and that's what we will start with. But there's also a cylinder, the surface of a cylinder, or a torus, or a sphere. And those also arise in nonlinear dynamics in natural ways, as we'll see later. But the clearest and easiest is to look at what people refer to as phase plane analysis. Where when we're thinking about a phase plane, we just mean we have two state variables, which we'll call x and y. So we have x dot is some function of x and y, and y dot is some other function of x and y. And that's the kind of thing we want to be looking at, where the f and the g will typically be nonlinear functions. So just some notation here. We sometimes write xy as an ordered pair. It's in the plane R2. We think of x dot and y dot as a velocity vector. Remember, that's our interpretation, that we're thinking of vector fields as a natural geometric picture for differential equations. And when I say velocity, I don't mean like velocity in mechanics. This just means a make-believe velocity that's happening in the phase space. We're thinking of x and y as positions. In that sense, x dot, y dot would be velocity. But really, I mean, x and y might be populations. They might be concentrations of chemicals. They're not really positions, only it's helpful to think of them that way. And so this gives us a vector field on the phase plane. Where, if you want to think of a little picture, if we have the xy phase plane, then the typical point is our xy, and sticking out of that point is a vector, x dot, y dot, that tells us if we were at this state, xy, at this moment, then in the next instant we would move in this direction with this speed. But of course then we'd be at some new place and we'd have a new vector there, and so we're going to keep following the vectors. That gives us the geometric picture of a trajectory moving on the phase plane. Or rather, I should say the phase point moving on the phase plane following a trajectory. So sometimes it's helpful to write this in vector form. Just to save writing, we might say x dot with a little underline on it to mean the vector version of x, where vector x refers to both x and y without the underline. So the vector version would say x dot is some function of x, with the x being in R2. Okay, now one aspect of this is we have to say something about the smoothness of these functions f and g. Remember that, for one thing, that's not the kind of issue we make a big deal about in this course. We will just assume that the f and g are sufficiently smooth that our systems will behave the way we want them to, like, for instance, that solutions will exist for the differential equation and they will be unique. So one condition that's sufficient to do that is if this vector field F is continuously differentiable. That is, F and its derivative are continuous. If we have continuously differentiable vector field, that's smooth enough to ensure then solutions x of t exist and are unique for any initial condition. So unless we have anything else to say about this, we'll just be assuming that we don't have to worry about existence and uniqueness. That'll just come automatically. Now that actually, I guess I should say first that I mentioned the word trajectory. So the picture here is that we have some state. We follow the local velocity. We're at some new place. Then there's another velocity there. We follow that. And just by following the local arrows, a solution to the differential equation will look like this kind of object that we're calling a trajectory. So a solution gives a trajectory on the phase plane. And I think you'll remember, because I tried to emphasize it at the very beginning of the course, that the whole approach in nonlinear dynamics is we want to understand the structure of these solutions without actually solving the equation. We're just going to try to do some other argument to see what shape these have and thereby get all kinds of information. Yes? The vector field is the interpretation of the differential equation. That is, when we have x dot y dot is a function of x and y, that is saying that at each point x, y, there's a vector. That's the vector field, the mapping from the xy plane to the vectors at each point. Right, so the vector field is that, but then the trajectory is the analog of the solution of the equation, with the property that at every point on the trajectory, the local vector defined by the vector field will be tangent to the trajectory. Okay, so you're just going to follow the arrows. The first step in finding a trajectory, you say, would be to draw the vector field. That's one way of thinking about it, and certainly that's how a computer would do it. It would draw it would calculate the vector field, and then you could integrate along step by step. Yeah, now we'll have better ways of thinking about it than just doing that. But that's essentially the idea, yes. Okay, so let us, is there any other question? Here I want to emphasize some things that this existence and uniqueness statement imply that you maybe wouldn't have thought of. But they'll be very important for us in everything else we're going to say. The main implication is that given uniqueness of solutions, trajectories cannot cross each other. And that's a pretty important property. That is, trajectories can't cross. So if you're looking at a phase portrait, as we call it, that is a picture of all the qualitatively different trajectories for a vector field, you'll never see something like this. A trajectory and then another trajectory going through it. That's impossible. And the reason it's impossible is, think about what it would mean if I concentrate on the crossing point as the initial condition, it would say that I have two possible futures starting here. I could either go like that, or I could go like that. That would violate uniqueness of solutions starting from that point. Right? There'd be two solutions starting at that point, and that's not possible by the theorem. I'm not proving that theorem, but in a good course in differential equations, you would see a proof of the existence and uniqueness for differential equations. So trajectories will never cross. We never have a picture like that. And now you might wonder, what about at a fixed point? What can happen? Well, it's true. Trajectories can approach the same fixed point. So in that case, you will have a picture that looks similar to that, but it might be, say, you have a trajectory coming in, here's a fixed point, some other trajectory coming in, and another. That is all perfectly legal because there's no contradiction. If you're at the fixed point exactly, then you just stay there. That's what it means to be a fixed point. These other trajectories don't actually touch the fixed point. They're just approaching it. You might say at infinite time, yes, they would touch it, but for any finite time, they don't. So, so there is no contradiction, and this is, common, a sort of picture we'll see frequently. Another thing, so maybe I should say, now in the case of these two-dimensional systems, the condition for a fixed point that'll be a point xy where x dot equals 0 and y dot equals 0 simultaneously. So both components of the vector field are 0 there. Or if you want, in the vector notation, you could say, well, the vector f at x star is 0, meaning the 0 vector. So that's another way of looking at it. Anyway, so that's a condition for fixed points in 2 dimensions. And back to this comment about the trajectories not being able to cross, here's an example of a topological consequence of that is interesting. So there are all kinds of strong consequences of non-crossing of trajectories. So if we're thinking still in the plane, as opposed to some other two-dimensional space, what if we had a picture like this? Suppose we have what we're going to call a closed orbit or a closed trajectory. That is, it's a trajectory, but it happens to close on itself. And so if you imagine the state of the system, the state will move around and then keep going and eventually come back, at which point it will return to its starting point. And then it will do the same thing it just did, and we'll do that over and over. That is, a closed orbit like this will represent a periodic solution of the differential equation, or a repeating motion of the system in a cycle, in other words. So a closed orbit like this is going to be the geometric counterpart of some periodic behavior. But now imagine you have something like that. Then think about what happens to some other trajectory that's trying to get inside. You can see that's not possible, right? There's no way for this to get in there without crossing. So, and likewise, if you have a trajectory in here, think about what it can do. If it keeps wandering around, well, one thing is it could approach a fixed point. That's fine. But suppose there aren't any fixed points in there. Then this trajectory has to keep going around and around, and it starts to get into trouble. Can you see? It can't cross itself, and it also can't cross this closed orbit. So what will it do? I mean, what was your suggestion? Go back and close on, go back, what, go backwards?
No, like
close on itself? So you're saying you think maybe inside a closed orbit, this trajectory would have to itself close? Maybe. That could happen. Yes? What else? Go ahead in the back room. It could asymptotically approach the closed orbit. That's another possibility. Yeah, yes? Could it make a fractal pattern? That's an interesting thought. That it could just kind of keep getting nastier and nastier. That, I think, will not be possible under our assumption about the f being continuously differentiable. Because that would start to get very kinky, and yeah, our f won't permit that. But that's an interesting thought. And we will see, though, that in 3 dimensions, as opposed to 2, when we start talking about chaos, not so much that the trajectories themselves make fractal patterns, but they can approach sets that are fractals. So that's an interesting thought. That's not far off. But anyway, back in R2, for our smooth vector fields, you can see that these periodic orbits will put a lot of constraints on what the other trajectories can do. So this can never get inside. And that's an interesting thing, that in the plane, a closed orbit acts like a barrier. But I emphasize that's a property of the plane. That is, that would not be true, well, actually it would be true on a sphere. It would not be true on a torus. Right? I mean, in the plane, the closed orbit separates the plane into an inside and an outside. But on a torus, a closed orbit doesn't necessarily do that. So we'll see. Anyway, it's going to be interesting when we look at other phase spaces. Yes? Let's see if I understand the question. The question was, is it possible that by changing the system slightly, the closed orbit that was the trajectory that was approaching the closed orbit could, did you want to suggest, could merge onto the closed orbit?
Yeah, like actually
truly get onto it? Yeah, that's not possible. So if you think about that, that would also violate uniqueness, because if this trajectory could actually merge onto the closed orbit, then think about the first point where it merged, and then imagine running time backwards. Then that point could either stay on the closed orbit or could go back off of the closed orbit. Right? That wouldn't be possible by uniqueness. Because you also have uniqueness in backward time as well as forward time. So trajectories never merge in the sense that they actually, one will become on top of the other. They can't cross and they can't merge. You had a question too? Yes? There was a similar question. Okay, and your question? Is this XY space? Yes, I'm still thinking in just the plane, in XY plane. This one in here? Well, what will probably tend to happen, I mean, as we discussed, it'll either, this orbit will eventually close to form another closed orbit, or it will spiral out to this original closed orbit, or if there are fixed points inside, it might approach a fixed point. Well, this is something we're going to later discuss called the Poincaré-Bendixson theorem that tells what the fate will be of such a trajectory. Yes?
Can they get infinitely close to each other?
Yes, the trajectories can get arbitrarily close to each other. If the longer like if this one was asymptotically approaching the closed orbit, it will get closer than any specified amount. That's allowed, sure. Okay, now I keep harping on the fact that this is in 2 dimensions. In 3 dimensions, you might notice, a closed orbit does not separate 3-dimensional space in any way. It doesn't act as a barrier. So a trajectory starting inside can kind of come out into the 3rd dimension and loop around, can make links. And that's part of what causes complications in 3 dimensions that don't exist in 2 dimensions. Okay, so we're getting ahead of ourselves. Anyway, just to summarize that one remark, that in R3 as opposed to R2, trajectories can intertwine. And in some cases, this may lead to chaos. But in 2 dimensions, there is no chaos. This is kind of a theme of the course, that we've seen in 1 dimension, behavior is very restricted. All you can do is go to a fixed point or go out to infinity. In 2 dimensions, you can go to a fixed point, you can go to a periodic orbit, or some other slightly more exotic things that we'll discuss. But you can't do chaotic motion. Whereas in 3D, that's the first place it can happen. Yes?
You're saying even with a linear system of third order, you can still have chaos?
No. The question was, could a linear system have chaos in 3 dimensions? No, of course not. Right. We know the behavior of linear systems. We're going to, in fact, discuss linear systems next. But no, I meant to say, that's why I say it may lead to chaos. It depends on the nature of the vector field. Some are chaotic. We'll give chaotic solutions, some not. Okay, so let us just state our goal for the next part of the course and then get down into the discussion of linear systems. Which I don't want to spend long on because, of course, we're discussing nonlinear dynamics. And you may have heard about linear differential equations somewhere else. So I'm just going to give you the essentials on that and then move on. People who came in late, we did collect homework. So at the end of the class, please put your homework up here, but don't do it now. So the goal then for us for the next several lectures will be, given a vector field or a system, however you want to think of it, x dot is f of x, we want to deduce the phase portrait meaning the picture of all the qualitatively different trajectories and we want to extract qualitative info from them, meaning things like existence and stability of fixed points and closed orbits. And so that's what we're going to try to work toward. Now, the first thing to do is to discuss the fixed points. They're the easiest objects. And for that purpose, we're going to use linear systems. That is, we talked a little bit about how in 1 dimension, it was so easy to draw the pictures that we could understand what was happening at a fixed point graphically. But in 2 dimensions, it would be a little harder to do that. So we're going to resort to linearizing around the fixed point and using linear systems information to tell us what happens in the neighborhood of the fixed point. And so that's our real reason for looking at linear systems right now. So this would be chapter 5 in the book. Let's jump there to linear systems. I think I might skip chapter 4, depending how much time we have today. If we have some time at the end, I might talk about chapter 4 quickly. But it's so similar to the earlier chapters. That was about vector fields on the circle, as opposed to the line. So the circle is another one-dimensional space, different from the line in that you can, by going in one direction, you can come back to your starting point. Not true on the line. So actually, the first place where periodic orbits occur is the one-dimensional thread of the circle. And so you can read about that in Chapter 4, but that's really basically the only new thing that happens in that chapter compared to what we've been discussing. So I think I'll just let you read that, unless we have a few minutes at the end. But okay, Chapter 5 on two-dimensional linear systems. So we could write them as x dot equals ax. And I mean, if you want to compare this to standard language, I'm speaking of linear systems with constant coefficients, and they're homogeneous. That is to say, I'm only going to consider systems of the form x dot equals ax, where A is a matrix of constants, A, B, C, D, and they're real. And so for a system like this, the origin is a fixed point. It's a fixed point for any choice of the matrix A, B, C, D. That's clear. If you just take 0, the 0 vector, A times 0 will be 0. And so x dot is 0 at the origin. So that's always a fixed point. But the question for us is, what's the phase portrait like in the neighborhood of 0? And I don't really know what you know about this, whether you've studied this kind of thing. In some linear algebra courses, they will go into some detail about this. Can I do a little poll of what you've had before? Have you ever studied this kind of system, 2-by-2 system of linear differential equations? Put up your hand if you studied that. Okay, just about everybody. Some people may be a little hazy on it or may not have studied it, which is okay. I don't assume you have studied it. But I'm not going to go into it really in any great detail. I'm going to try to just summarize the key points. If you find some things confusing or you want more information, you should look at either a differential equations or a linear algebra book. But I'm only going to spend today on this, and then we'll move on. So what we're interested in is the phase portrait near the origin, and that's going to be determined by the eigenvalues and eigenvectors of A. Which is one reason that you learn about eigenvalues and eigenvectors in a linear algebra course. They're crucial for studying linear differential equations. So to motivate, why would the eigenvectors and eigenvalues come into this? Let's think about it this way. You could say, in the style of a physicist, let's look for a certain very special kind of solution of this equation. That is, rather than trying to solve it in general, let's restrict to solutions that move along a straight line in the plane. So that is, I'm going to seek straight line solutions, meaning that all they can do is, they just go like that. Not necessarily at uniform speed. They might, in fact, speed up or slow down, but we're just going to look for that. So, in fact, let's look for x of t vector is a constant vector v. So v refers to this direction. And I don't just want a constant. I want some time dependence. And from knowing a little bit about linear systems, you could guess that exponential time dependence is a reasonable thing to try. If you don't want to do that, you could put in a function of t, and then you'll soon realize it has to be of this form. So just plug in something that looks like that. And then x dot for this class of solutions, if they exist at all, would be x dot would be V is a constant, so it just stays there. Then by the chain rule, you'd get e to the lambda t times lambda. And on the other hand, AX, which this is supposed to be equal to, is just A V e to the lambda t. And since A is a linear operator, that is, it's represented by this matrix A, then when I take A of this scalar, this scalar, e to the lambda t times the vector v, the e to the lambda t comes outside, and it's e to the lambda t av by linearity. And so what's nice about this is now you can see that this has an e to the lambda t, that has an e to the lambda t. And so solutions of this type will exist if AV equals lambda v. So such solutions exist if we can find a v and a lambda such that AV equals lambda v. And you'll recognize that as the defining equation for an eigenvector v with eigenvalue lambda. Okay, so we would have these straight line solutions if such a v and a lambda exist. And now, do they exist or not? Well, you know, then it becomes this linear algebra question of trying to calculate the lambda and the v. So lambda is given by determinant of a minus lambda I equals 0, I being the identity matrix. And if we write that out for our little 2x2 system, that's going to be a minus lambda b c d minus lambda, where the vertical lines mean determinant. And then calculating that determinant, this comes out to be lambda squared minus tau lambda plus delta, where I'm introducing notation that we're going to use frequently, that tau is the trace of this matrix. Given by the sum of the diagonal elements in the matrix A, that is, it's A plus D. And delta is going to be our notation for the determinant of the matrix, which would be AD minus BC. So if you don't see that, just multiply this out. This expression times that expression minus C times B. And, you know, after you do a little bit of algebra, you'll get that this is the characteristic equation for this problem. And so now we can calculate the lambdas implied by this. It would say it's a quadratic equation that we're trying to solve. So lambda is negative b, which in this case, I mean negative b. I'm doing the quadratic formula for memory. B is negative tau here. So this would be tau plus or minus the square root of tau squared minus 4 delta all over 2. And there's some useful little facts to keep in mind for some things we're going to say in a minute, that it's a nice property of the trace that it's the sum of the eigenvalues. So think of this as two eigenvalues, lambda 1 and lambda 2, depending on the plus or minus. So if you add these two, the square roots cancel out, and you get that tau is the sum of the eigenvalues, and the determinant is the product of the eigenvalues, which are facts you may have heard about in linear algebra. Okay, so is there any question about anything at this point? No? Okay. So then let's talk about the possibilities for what these phase portraits will look like depending on the details of the lambdas. Right? I mean, that's the issue. Or the way that we'll tend to phrase it is the trace and the determinant are very handy. Rather than going all the way into calculating the eigenvalues themselves, just from knowing the trace and determinant, we can say a lot. So here's a quick run through the classification of the fixed points. For this group of two-dimensional systems here, x dot equals ax with x in R2. And there are a lot of cases which at the end I'll summarize in a big diagram. But for now I want to just kind of grind through analytically case by case. The simplest of all, I would say, are the saddle points, which you can spot immediately because they're the only ones with negative determinant. So if you just calculate the determinant for your matrix and it's negative, you're done almost. It's a saddle point. That is, if you have a negative determinant, then one of the lambdas will be positive. Let's call that one. That is, let's look at our formula over here. Suppose delta is negative. When you look at the square root, you have tau squared minus a negative quantity. So the thing inside the square root will be positive. Right? There's no issue of imaginary or complex roots. So then by just evaluating this, you can calculate or check that one of the lambdas is positive and one is negative. And therefore, they're distinct. That is, they're not equal. One's positive, one's negative. And there's a nice theorem in linear algebra that when you have distinct eigenvalues, you have two eigenvectors that are linearly independent. So the eigenvectors that go with these eigenvalues, v1 and v2, are linearly independent. That doesn't mean that they're necessarily orthogonal. They just are not on the same line. So let's draw a picture of them. Say one of them looks like this, and one like that. Those are the span of the two different eigenvectors, that is, all scalar multiples of each one of them. And now, on the one where there's a positive lambda, well, maybe I should say it this way. If we write the general solution for x, we already said that we were able to write down these straight line solutions, a constant vector times an e to the lambda t. The general solution will be a superposition of those eigensolutions. You'll get a constant e to the lambda t that's lambda 1. That's the behavior in the along the v1 direction. And then plus another arbitrary constant e to the lambda 2t v2. So hopefully that looks familiar, that the general solution is a linear combination of these eigensolutions. And so what that will mean in our picture is that if we were confined to the, say, the first eigendirection, which is the one with the positive lambda, then we're going to move on this straight line away from the origin. So we already can see that the origin is unstable in the sense that these trajectories going just along these straight lines, this straight line, they're going away. But on the other hand, the other eigendirection, so this one with the lambda 2 negative, those are exponentially decaying because they have e to the lambda t with a negative lambda. They're coming in. And so this is a typical thing at a saddle point, that you've got some directions coming in and some going out. And then the other trajectories, which are not these straight line trajectories, will look kind of hyperbolic. That is, they would come in and then go out like that. And then the ones on this side would go sort of, you know, like that, or like this, or like that, where I haven't drawn it very well, but you should be thinking about the asymptotic behavior at long time, either time going to plus infinity or time going to negative infinity. As time goes to plus infinity, a trajectory like this would asymptotically approach this straight line, that asymptote, in fact. And in backwards time, it will asymptotically approach this one. Okay, so that's a picture near a saddle point. Is there any question about that? We'll sometimes speak of this kind of straight line as being the stable eigendirection. And the other one is the unstable eigendirection. I don't like it when the writing gets on top of itself. So put a little closed orbit around the whole thing. No, that wouldn't be possible, actually. That picture, it turns out, is not possible, so I'm not going to put the arrow on there. All right. Okay, so that was the saddle point. That's case 1. Case 2 is attracting and then if you want to think sort of its doppelganger but backwards are the repelling fixed points. So in the pictures, I'm going to show just the attracting ones. The repelling ones look the same topologically, except all the arrows are reversed. So let's just focus on the attracting case. Reverse the arrows for the repelling ones. Well, then there's a couple of flavors of attracting fixed points. So we have to have subcases. But what characterizes the attracting ones is that they have a positive determinant but a negative trace. The repelling ones have a positive determinant but a positive trace. So let's now look at, as I say, there's sub-flavors or whatever. So case 2A are what we'll call nodes. And what controls them is the square root. So a node will have a real square root. That is, tau squared minus 4 delta is positive. And so in the case where we have this tau squared minus 4 delta positive, then you can see that both the lambdas are real. And so they have the same sign. That is, they're either both positive or both negative. And since we're interested in the attracting case, let's consider the possibility that they're both negative. So let's suppose that we've got lambda 1 is more negative than lambda 2, and they're both less than 0. Well, we have distinct eigenvalues again, right? There's different lambdas. At least I'm supposing that for now. I'm going to suppose that they're distinct. We'll talk a minute from now about what happens if they're repeated negative eigenvalues. But let's ignore that. That's kind of rare. I'll get to it later anyway. But so suppose they're distinct and negative. Then, again, we have V1 and V2 linearly independent. And so again, we can draw this picture with our two eigendirections, except now we're coming in on both of them. So now we'd use a big fat solid dot there for the origin that's stable or an attracting point. But what about the other trajectories? And this is a point that often people find confusing. And if you start poking me, I'll probably give a confusing explanation of it. So I don't know if you want to see that spectacle, you could. But so all right, the question is, what do the other trajectories look like? Like in particular, let's suppose that this one is the V2 direction along here. And I don't mean that this whole line is V2. This is supposed to be all scalar multiples of V2. So it's the eigenspace corresponding to V2. And then this is the V1 direction. And we said that we're thinking of lambda 1 as more negative. So that will mean that the decay is faster along this direction. Let's put two arrows there to indicate that this is the fast decay. This one has slow decay. Just, one compared to the other. One has faster exponential decay than the other. So the slow direction is the V2 direction, and it's slow, because lambda 2 in absolute value is closer to 0 than lambda 1 is. Okay, so anyway, we've got this slow direction. And so now, what do the trajectories look like? Well, maybe this will seem plausible, I hope. That is, if I start somewhere typical, kind of influenced by the two decays, but think of decay as being fast in this vertical-ish direction. So you're going to kind of go like this, and then slowly come in this way. I drew it as if it merged, but it doesn't merge. It's just asymptotically. Maybe I better put a little bit of daylight there. I wanted to say I come in and then slowly ooze my way in along this direction. And likewise over here, you kind of go zap and then slowly start bending your way in like that. Likewise down here. So I've exaggerated the picture a little, but if you draw these on the computer, you'll see that that's kind of qualitatively what's happening. By the way, maybe this is a good place to say that you have to use computers in this course. We've mentioned that before. But for drawing pictures like this, a very handy program is called P-Plane. And you can find it on the web. Just type in P-Plane, it'll come up. And there's a Java applet that you can just run right in your browser, or you could download it and run it inside of MATLAB or whatever. But so anyway, so that's the picture near a stable node. That's what we would call this kind of point. And also, just two other things to say that I sort of indicated by the sketch, but maybe I ought to record, that as t goes to plus infinity, the typical trajectories approach the fixed point x star, which here was taken to be the origin, tangent to the slow direction. That's my point. That's what I was trying to draw. Whereas in backwards time, that is, if I want to think about what happens as I go back this way, they end up being parallel to the fast direction. So in backwards time, as t goes to minus infinity, trajectories get parallel to the fast direction. Okay, now, did you have a question?
So if V1 and V2 are perpendicular, would these form parabolas?
The question was, if V1 and V2 are perpendicular, would these be parabolas? Not necessarily. They certainly will look kind of like parabolas, but that would depend on exactly what the ratio of the eigenvalues is. You could check, for instance, if you had a matrix that looks like this. I mean, let's suppose it was already diagonalized. You had something like that. Right, I think if you have that, then I have a feeling that might give parabolas. You could check that analytically by just calculating what's happening. I mean, actually, we could do it trivially, can't we? It's going to be x would be x0 e to the minus t, and y will be y0 e to the minus 2t. So you can see that, you know, y will be proportional to x squared, because x squared would give me e to the minus 2t. So there it would be what you said. It would be a parabola. But if this was a 3, then I think it won't be a parabola, right? So, yeah. Is there another comment or question? Yes?
If it was a 3, would it have a cubic function?
If it was a 3?
Yeah.
Yeah, I got a little nervous about that myself. So if it were a 3, I mean, we don't believe it's going to be a cubic because it can't do that. It's going to, what is it going to do? Should we quickly grind it out? It can?
Because the derivative would be 0.
Oh, okay. Yeah, I guess so. Is that right? Really?
Because then it would also be reflected around.
Yeah, okay. Aha. So there will, I mean, I wouldn't actually flow through the fixed point, but yes, there will be a cube. So there'd be a family of cubics all going through that point, and then pieces of the cubic would represent these curves. Yeah, that's right, isn't it? I think so. Okay. All right, so let us move on then to the next case. That was case 2A. One thing you might want to realize, though, is everything I've said here works for the repelling case as well. I focused on the attracting case, but if you wanted to do the repelling case, you would just put all, like I said, reverse all the arrows, make this down arrow up, all of them just reverse. But it's still true. I mean, I phrased this in a way that it works whether it's attracting or repelling. You always approach or move away from the fixed point tangent to the slow eigendirection, and then become parallel to the fast eigendirection in the other direction, you know, like say up here. All right, so that was case 2A. 2B. These are spirals. And they have positive delta, just like, because that's what makes them case 2, that they have positive delta and negative trace makes them attracting. This is fine, but then let's suppose that the tau squared minus 4 delta is negative. So now we have complex roots, complex lambdas. And there are not going to be any real eigenvectors. We're not interested in complex eigenvectors as far as the phase portrait. It's only the real eigenvectors that will show up. The eigenvalues are certainly distinct, being complex conjugates. Lambda 1 is not equal to lambda 2. Let's call them, say, mu plus or minus I omega. So this case is a little tricky to write out explicitly. But again, I guess I'll refer you to a linear algebra textbook or a differential equations textbook. All we're going to need to know about this case is that this mu and omega have nice physical interpretations. That you should think of the mu as, you know, in the case where, let's say, mu is negative, which is what we're interested in, the attracting case. Mu negative controls the decay rate, and omega controls the rotation rate of the spiral. If you want to write out the solutions for x of t, they're going to from linear algebra can show that each component of x of the vector x is a linear combination of things that look like e to the mu t cosine omega t and e to the mu t sine omega t. That is, this kind of expression will look familiar to you if you remember when you studied the damped harmonic oscillator, that you have things that have exponentially decaying envelopes and then sine or cosine of some oscillating omega t term in there. So the spiral then is this geometric counterpart of a damped oscillator. And what the pictures look like in the xy plane is something like this. A typical trajectory might look, you know, like that, which is, of course, why we call it a spiral. And then some other trajectory, you know, starting somewhere else, just does the same thing. Comes in and spirals in. Now, one question that people often have is, how do I know which way it's rotating? That is, I've drawn it here as though the rotation is positive. That is, it's a, oh no, I guess I wouldn't say positive. It's in the clockwise direction here. How would I know that? For that, you don't get that information from tau and delta or from the lambdas. You have to look at the vector field to see this. So I guess what I would recommend is just calculate one vector at some point. And, you know, if you see a vector that looks like this, then you know that it's going to be rotating that way. It really, just calculating one vector will be enough to give you the sense of the rotation. So as we do examples of these, I mean, I can show you more concretely what I'm talking about. Yes?
So analogous to the case right before this, where there was like stable and unstable nodes, and they're like stable and unstable.
Yes, so the question was, can there be, just analogous to how there are stable and unstable nodes, can we also have stable and unstable spirals? Yes, definitely. So again, you could just reverse the arrows. So an unstable spiral will be something that qualitatively looks like this. And if you wanted to translate that into a time series, that is, you can think of this as the, you know, x, this as y. If you were to graph x versus t, an unstable spiral will have a time series, you know, that looks like that. It's a growing oscillation. Yes?
Also, another question about the difference between unstable and stable. So for a stable node, it makes sense that you like intuitively that you start at a point and then you sort of approach that fixed point as time progresses, and like so you think that like at time infinity you sort of just about reach the fixed point. What for the unstable case, it's a little less easy to put the graph like dark as finite.
The question is, so if I get your question, you say if you think about a stable point for a node, then what we should think of is something which is just decaying to the node, which in time series speak would sort of just look like that. It's just monotonic decay to a node. Whereas, that is just damping out to an equilibrium without oscillating. So this is more analogous to the overdamped case in mechanics. But then you're wondering what would that look like if it was unstable, but that just looks like exponential growth. More or less. You don't see that from the picture. But it is. I mean, both of these, which were exponential decay along the two axes at different rates, this will be a sum of two growing exponentials. So that's not anything very mysterious. Let me move on, though. I want to finish this off today to talk about two other cases and then a diagram. Yes? Last question for now. Excuse me? Oh, I drew it as a sort of symmetrical spiral. That is not always true. No, you should draw the spiral as more elliptical. That's a good point. Yeah, I mean, a typical stable spiral would look probably more like this. Yes, thank you. That's a good point. And there's no reason that it has to have any particular, I mean, like I've tried to draw it with a, you know, like a skewed tilt to it there. Okay, so those are the cases of spirals. Then there's a very special case of a spiral, which is if this damping rate, mu, happens to be 0. So that can happen. And let's see what that does for us. So that's a next case, which is case 3, which is traditionally called a center. That's where you have a positive delta, a trace that happens to be exactly 0. And in that case, the lambdas are pure imaginary. They're just plus or minus I omega. There's no mu. The mu is 0. And so when you have a center, then the trajectories, every trajectory is closed. And they're all going to look elliptical. So a typical picture might look sort of like this. And these are all going to be rotating in the same direction. So we'll see this, the most famous case of this would be if you drew the phase portrait for the simple harmonic oscillator with no damping. That is, just convert the system x double dot plus x equals 0 into a phase plane picture. That would, in fact, give perfect circles, the way I've scaled it, where this is x, and then this would be y defined as x dot. Except I think I've drawn, let's see now. It looks like I have that upside down, don't I, in terms of the arrows. Do I? Because, yeah, I think that's not right. Here, maybe this is a good place to illustrate how to draw the arrows. Hang on a second. Yeah, why don't we just draw one? We could do this by hand. That is, if we had x double dot plus x equals 0, we could convert that by saying y equals x dot. Then we'd have x dot is y, and y dot, which is x double dot, would be negative x. So drawing the vectors at some places, like when we're here at a positive x, the y dot is negative, but the x, I'd have vectors that look like this. And then here they'd go like that. And this is going to actually have circular trajectories. So maybe I was right in the first place. I drew it going, which way did I draw it? No, I drew it wrong. So the arrows should be going clockwise. And that should make sense, I hope. That is, when you're in the positive x half plane, this says y dot is negative x, therefore it should be going down. That is, in the positive x half plane, the arrows have a downward component. That's enough to show you that you're rotating that way. Yes, you had a question?
In this case, is it possible for any of these paths to approach a fixed point?
Can these paths approach a fixed point? No, they're all periodic. Every trajectory is closed, so every trajectory closes on itself and does not approach a fixed point. There is a fixed point at the origin, but any other trajectory is a closed orbit around it. So this represents perfectly periodic motion, and also with the property that for any initial condition it's periodic. We'll see that that's not very common in nonlinear systems unless there's some further structure like a conserved energy or something. But it can happen very easily in these linear systems. Yes, one more?
Just one more.
All right.
So, is it always going to be the case that these orbits are always centered around the fixed point?
Is it always the case that the orbits are centered around the fixed point? Yes. Yeah, I don't know exactly what you mean by centered, but they will enclose the fixed point. Okay, you're up. Yes, go ahead.
So the radius of these circles is basically the amplitude of the oscillation?
Yes, the radius of the circles, or in general of the ellipse, will reflect the amplitude of the oscillations in, if you want to think mechanically, in the position and velocity. Right. That's right. Okay, so case 3 was centers. Case 4 is a pretty bizarro case, which is what happens if delta is 0? I've been assuming it was either negative or positive. But if it's 0, then, okay, that means the matrix has determinant 0. And so now, when we're solving AX equals 0 to look for fixed points, we don't have a unique solution anymore. You have 0 determinant. You could have a whole line of fixed points or a plane of fixed points. A plane of fixed points would mean every point in the plane is fixed. That's a really boring dynamical system. That's x dot equals 0. Wherever you are, you can't move. That's an easy one to analyze. But it's pretty unusual. Doesn't come up too much. Sometimes you will see a line of fixed points, and so those will look sort of like this. Think of every point here as fixed, although I've only drawn 4 or 5 of them. But other directions might asymptotically approach those, say like this. you could have something like that. Okay, this is very uncommon, but it can occur. And so when we have this, we might speak of non-isolated fixed point. At the origin. Because in the immediate neighborhood of the origin, there are fixed points next to it. Okay, now for the grand conclusion. Since it's a lot to remember all this stuff, here's a simple diagram that summarizes all of it, which is, in terms of the tau and delta variables that we defined, we can see what's going on if we draw this parabola that we talked about, where tau squared minus 4 delta equals 0. That is, we know that that's a special condition because that's the dividing line between nodes and spirals. Actually, I didn't really talk about what happens on that line. That's when I would have repeated roots. And so let me refer you to the book to see what happens there. You can get some degenerate kinds of nodes that maybe I'll just sketch them on the picture. But, okay, so in this picture, we have the saddles living over here. Where delta is negative. We have centers living on this axis. This is a very schematic picture, but I hope you understand what I'm trying to show. That the centers live here, where delta is positive but tau is 0. We have unstable spirals in here. Or then stable ones down here. The stable nodes would be down in this little space. So stable nodes way down here. Likewise, the unstable nodes are up here. So on this parabola continues. And what else? So then, bizarrely, this one point would represent the plane of fixed points. I'll write FPS for fixed points. Lines of fixed points could be somewhere else on this axis. And so that pretty much summarizes it. The only thing that's been left off was what happens exactly on this parabola. And so check out the details in the book. But what you can have on here is these degenerate nodes of two types. That is, they can look sometimes very symmetrical, where every direction is a straight line trajectory direction. So you can have something that is, the two lambdas are equal in such a way that, we have every direction is an eigendirection. So when we have this, we speak of a star, for obvious reasons, a star node. Or we can also have very weird ones that have one eigendirection. This is in the case where you have like a Jordan block, say something that looks like lambda 1, 0, lambda. This thing you can check only has one eigendirection, not two. And that will have a funky looking shape that looks sort of like this. You might be coming in, but then here you kind of almost try to spiral around but don't make it. And likewise here you do the same thing. And so all the trajectories do this kind of stuff. So I don't dwell on this too much because these hardly ever come up in practice. But in the mechanics context, this would be the case for, this case would be critical damping. You may have learned about overdamped and underdamped. These are the critically damped. They look like that. But they're pretty exceptional. The main picture is this, and we'll be applying that to nonlinear systems starting next time. Okay, thank you.